Imagine being around when the electron was discovered. Scientists were only beginning to figure out how an electron could be used, and they certainly couldn't have predicted all the ways we use them today. Who cares if electrons can power a streetlight? I want to share how my cat plays the piano. Many of you have asked us what neutrinos can do, or what we could use them for. That is a great question, and it's what we're talking about today on Even Bananas. Neutrinos are still really hard to detect, and they require some enormous advanced detectors. But for a moment, let's dream big. A neutrino's superpower is its ability to pass through solid matter. That makes it an amazing messenger. So you might be able to guess one pie in the sky application for neutrinos: communication. Imagine trying to get a message from New York to Tokyo. Traditionally, signals would have to travel through cables along the Earth's surface, but neutrinos could happily travel in a straight line, directly through the Earth. No tunnel or cable required. You could even imagine using neutrinos to send messages out into space, without worrying about them being deflected or absorbed by anything along the way. It's a nice idea, but it doesn't really work with today's technology. One of the problems is that neutrinos rarely interact, and the neutrino beam spreads out as it travels. That means we can't actually detect enough of them to make them useful for transporting messages. For example, in the NOVA experiment at Fermilab, scientists are sending trillions of neutrinos 500 miles from Fermilab to Minnesota. And in Minnesota, they see less than 1 neutrino per day. So the neutrinos might get there quickly, but you'd have to wait a while to receive enough to make out a sentence. Amazingly, researchers at Fermilab have already successfully sent a short message using neutrinos through 210 meters of solid rock. As expected, the neutrinos were fast, but gathering enough data and decoding the transmission was slow. It took the 170-ton Minerva detector about 2 hours to receive 8 letters. The first word transmitted by neutrinos? Neutrino, of course. So it seems like we're a long way off from a neutrino cell phone. But what about tackling something a little simpler, like world peace? Okay, not quite world peace, but close. Nuclear non-proliferation. Nuclear reactors produce a lot of antineutrinos, and as we know, no amount of shielding can stop them. That means neutrinos could potentially be used as a tool in nuclear security. You can imagine using neutrinos to monitor or discover nuclear reactors, or to verify that treaty agreements are being adhered to. You could potentially keep track of how much uranium or plutonium is present in a reactor, because these different elements produce neutrinos at slightly different energies. So neutrinos might warn officials about the illicit production of plutonium that could be used in nuclear weapons. There are a few different ongoing projects to research using neutrinos for nuclear monitoring, including a US-UK collaboration called Watchman. In a similar vein, geologists could use data from geoneutrinos produced by radioactive elements inside the Earth to better understand what's happening inside our planet. The Camland and Borexino experiments have already done this a bit. They're able to see neutrinos from uranium and thorium, but not from another major source, potassium. That would require a different, more sensitive detector that could capture neutrinos with lower energies. Those are some pretty cool ideas. But realistically, we'll be adapting and using the technologies developed to study neutrinos long before we use the neutrinos themselves for anything practical. For example, physicists are developing machine learning algorithms to spot neutrinos, which have applications in other machine vision like medical imaging. And the light detection system we use for Dune has similarities to the light detection systems being studied for self-driving cars. Neutrino detectors themselves can also be used to study things beyond neutrinos. For example, the IceCube experiment deep in the ice at the South Pole has contributed to new discoveries in glaciology. And researchers showed how they could use the Antares neutrino detector in the Mediterranean Sea to study bioluminescence from deep-sea creatures. It's clear that our understanding of neutrinos is still in its infancy. Much like those who discovered the electron couldn't foresee how it would change the world, we don't know where neutrinos will take us. We do know that they are fascinating particles, and one of the best ways to try to answer some of the biggest questions about our universe. As for how they change the world, we'll have to wait and see. What other far-out applications of neutrinos can you think of? Let us know in the comments, and don't forget to like, share, and subscribe. Fun fact: many neutrino detectors built for physics research are really big, and they're often underground to shield them from muons in the atmosphere. But some of the detectors being developed for nuclear reactor monitoring are a bit different. These detectors need to get up close to the reactor and move between different sites. Researchers on experiments like Prospect have recently shown success making above-ground mobile neutrino detectors that can accurately measure neutrinos at commercial reactors.